First of all, thanks for having me here and allow me to talk what I am doing. I also teach undergraduate level courses on climate change. So I thought maybe I could tell you something about what I teach to my students. Very basic things. I don't have a very nice pictures like the speaker has shown, satellite measurements, although I use all those measurements and estimate how much is the the implications of the changes happening around the globe on our environment, particularly on climate change. But today I will just talk very basic things like we talk always and hear the climate is changing, but then we also hear how much, and what are the causes of climate change. I'm quite sure that David Archer has already covered some of the basic things which I'm not going to cover here, but the issue about the uncertainty is a very big issue when we take any action. So I just want to touch this issue today and talk about what do we mean by the uncertainties, from where this comes from, in our Earth's climate system, and how do we actually estimate that uncertainty? What do we mean by uncertainty? So this is my research interest. That's what I do in my research group. I study the interactions of the climate system with the climate change. Okay, interactions. So these are all interactions. When we talk about the change, we always say about 0.5 degrees Celsius temperature change has so far occurred since around 1800 or so, and it will change by around 1.5 degree to 3.5 degree. So it's a big, the uncertainty range. So now, if the policymaker talk about, okay, what are the implications of 1.5 degrees Celsius on our biological, or biology or our agriculture system or the water resources, and what are the implications of the 3.5 degrees Celsius? So it's a large uncertainty range, and we need to understand why do we have this uncertainty range? How should we reduce the uncertainty? It all involves not only the science, but the socio-economic aspects, okay? And the populations, as some of the other speakers also talk about. So interactions is very important, and I'll just talk about today what I mean by interactions. So I have a list of things which I'm going to cover. I'm not sure how many topics I'm going to cover, starting from what drives the Earth's climate system. I'm sure that David has already covered this topic. Then we talk about the greenhouse effect. I mean, this is the natural phenomena, but what we are concerned about, not a greenhouse, but the enhanced greenhouse effect, okay? And that's briefly I will touch base on. And then relationship between the feedbacks, interactions, okay? What do we mean by interactions? How do we estimate those interactions and the uncertainties in our climate system? And then we talk about carbon cycle, okay? CO2 is a major greenhouse gas. What drives CO2, okay? How it is changing in the atmosphere. Humans are perturbing our system, but not all emissions that humans are emitting goes into the atmosphere. Part of it remains in the atmosphere, rest goes in some other reservoirs. So I'll touch base on this issue as well. And then I will talk about the models, okay? I have developed a very simple model, very simple model, which you could use in your classroom to teach about the science of the climate change. And it is available on the web, and I will show you some exercise which you could do and teach about the science of the climate change using this model, which is available on the website. And I have already connected to the internet, and I could show you where you could download. I mean, you cannot download. It runs on my server, but you have a interface. Through that interface, you can make a lot of things. You can give exercise and all sorts of things, which I'm going to briefly discuss. Okay? And that's pretty much it. And if time permits, I can answer this question. Okay? Okay. So let's start with this, the basic problem. How the climate is driven by the human activities and how it goes from one component to other. So we talk about the greenhouse gas concentration which come from the human activities, and then we emit and it converts into the concentration. So this is the first step. Okay. The second is then the impacts of the climate in terms of the precipitation, temperature, sea level rise, and then we have a human health impacts. For example, and ecosystem impacts, water, hydrology, all those impacts. And then we go and talk about the emissions, okay? Because these are the driving force of all these impacts. So we need to control all these emissions, which come from the human activities in some cases, but also from the natural sources, okay? We always talk about the human activities, but I think we have to also emphasize there are some natural sources of all these gases. Plants also release number of gases which we have no control on, okay? There are a number of natural sources which also emit gases in the atmosphere. So no matter what, even if the humans control some of the emissions and control the concentration of the climate, but humans have no control to control the natural emissions, okay? I'm not going to go in more detail about all these, but all these components are studied in my research group, and I touch on several issues, okay? So when we talk about the climate change, it's not a one cycle, like I've talked about emissions, concentrations, temperature change, and then impacts and then emissions. There are a lot of interactions going on within the climate, Earth's climate system. When I talk about the Earth's climate system, there are a number of components: atmosphere, vegetation, land surface, ocean, ice, and all they are interacting. Okay? All they are interacting, and how they are interacting, we don't understand. I don't believe that any scientist can say that we understand how the climate system is interacting. And that's the bottom line. We don't understand how the climate system or components of the climate systems are interacting. Another aspect of this climate system is there are some causes of climate system, as I have mentioned, natural causes. Like you could say changes in plate tectonics. You know, the geologists can say that our continents are moving. You know, the mountains are, you know, the heights are changing. All those things, and also the physicists can say that there are changes in the Earth's orbit, okay, and also changes in the sun's strength. Right? All these are changing, but these changes are over a long period of time, in millions of years, and the impacts of all these changes are minor on our climate system. But there are certain changes which are making our climate quite different as compared to, say, for example, 200 years ago. And these changes are occurring due to the human activities. And I'm not going to go in more detail, but we always hear all the time the fossil burning, deforestation, reforestation, all these activities are having impact on our climate system. So what is happening? You have a natural changes, you have a human-related changes, all they are interacting with our Earth's component. Say, for example, I have already listed all those, and then you have a changes. Okay. So what happened is that they are all interacting. We don't understand how they are changing, how our climate is going to change in the long term. So the bottom line is we have to understand what are the implications of all these interactions. Okay. Okay. This is a basic thing about the climate change, greenhouse effect. We always hear climate change is due to the greenhouse effect. The solar radiation is absorbed by the Earth's surface, and then it releases long-wave radiation. Part of it is trapped by the greenhouse gases, and then it warms the Earth's surface. Okay, so this is the basic phenomena. It is natural phenomena. We are not concerned about the greenhouse effect. It's must. But what we are concerned about, the enhanced greenhouse effect. There are some basic fundamental principles of this warming. For example, all objects with temperature above absolute zero emit radiation, what we call the long wave radiation, no matter what, during the daytime and the night, and all the time, all the objects are emitting radiation. So the higher the object's temperature is, so there is a higher infrared radiation, more radiation in the atmosphere. So think about it, if the climate is warming, you warm the surface more, it will emit more radiation, then what is going to happen? More climate change. So it is a kind of feedback, okay? So it works in both ways. If the climate gets cooler, so you should expect less release of radiation from the surface, and then less cooling, okay? So it is a kind of feedback. Again, there are some other aspects of also this greenhouse effect. For example, Earth absorbs solar radiation, as I have already mentioned, only during the daytime, okay? However, it emits radiation, infrared radiation all the time, day and night. And what happened that water vapor and the CO2 are the two major important greenhouse gases which can actually enhance this effect. Okay, there are a number of gases we can talk about. For example, nitrous oxide, methane, chlorofluorocarbons, replacements of the CFCs, but these are the two major greenhouse gases. Okay, we always talk about the CO2, but you'll be surprised that the major greenhouse gas is water vapor, but nobody talks about that. Why? Because it's a natural, emitted gas. There is no human-related factor that emits the water vapor in the atmosphere, but this is the major greenhouse gas. Okay, and this is the major greenhouse gas, and we don't understand how it is interacting with our environment. For example, how the clouds are forming in a different part of the world, at what time of the the year the clouds are forming. All those uncertainties come from the water vapor. We understand very well how the CO2 is emitted, what are the implications of the CO2 in the atmosphere, but we don't understand the interactions of water vapor with other components of the climate system. Okay, just to give you an example, what I mean by the enhanced greenhouse effect or the interactions of the various processes, what we call the feedback mechanism. I have a very basic fundamental science, the principle here, which I want to show how the climate is working, how the climate system is interacting with various components, and what happens if you increase the CO2 concentration in the atmosphere, say for example, double the CO2 concentration in the atmosphere. Just example. Okay, so assume that we have a concentration of CO2 at a current level, which is about 380 parts per million by volume. Okay, once you have that and you have no change in the system except for the CO2 concentration, you just assume the system is in the balanced state. So in that case, you have an incoming solar radiation is balanced by the outgoing solar radiation at the top of the atmosphere. Okay, top of the atmosphere is around 50 kilometers. Okay, and we are around, our lower boundary is about 100 meters. So most of the changes will occur at the top of the atmosphere. So incoming solar radiation, outgoing solar radiation, which is what we call the long wave radiation, is balanced 240 by 240. Okay, and because of this balance, there is a temperature change around 1.5 degrees Celsius. Okay. So if you assume that there is no change and it will remain as it is, over the time the system will get balanced and you will have a temperature change about 1.5 degrees Celsius. Now what happens, you add the same amount of CO2 into the system, that you double the CO2 concentration. So what is going to happen? Okay, what is going to happen, because you have a higher CO2 concentration in the lower atmosphere, so you expect the part of the long wave radiation which is emitted to the top of the atmosphere will be absorbed by the CO2. Okay, so you should expect less long wave radiation at the top of the atmosphere. Okay, so then what happens? System will try to adjust this change. Okay, so in order to adjust what is going to happen, then the temperature will rise. Okay, as I have mentioned, higher temperature change means higher radiation. So in order to balance, the system will try to adjust the change. Okay, in order to adjust, the temperature has to rise because more radiation has to go up to the top of the atmosphere, as I have mentioned. So what you expect then, the temperature to rise about 1.2 degrees Celsius. It's assuming no interaction is occurring in the system. Okay, now you go back to the interactions, but in reality, it's not about the 1.2 degrees Celsius change, but it is about 2.5 degrees Celsius change. Or uncertainty is quite large in this change from 1.5 degree to 4.5 degrees Celsius. So this is the uncertainty range. Okay, from where this uncertainty comes? This uncertainty comes from the interactions, what I have just mentioned. The interactions, the feedbacks, water vapor, how the water vapor is changing, how it is forming the clouds, and how cloud is interacting with the climate change, how the oceans are absorbing CO2, how much is absorption, how much is the release from the ocean. All these feedbacks are changing our climate system. And we don't understand, uncertainties are very large, okay, in this change, okay. And that's from where we talk about the uncertainty, and the uncertainty comes from these feedbacks. Okay, when we always have a projection, always you will have an uncertainty range, and that uncertainty range comes from this 1.5 to 4.5 degrees Celsius. This is the uncertainty range, and I'm going to show how it's going to work using my model. Okay, okay. So what is this is called the climate sensitivity. Okay, so the climate sensitivity is nothing but a steady state increase. Steady state means if you have a system in a balance and you disturb the system and it goes to the same new state, okay, and then after that if you don't perturb anything it will remain at that state, okay. So that is your steady state increase in the global annual surface temperature associated with given global warming forcing. So forcing is watts per meter square, okay. So wattage per meter square, okay. So when you have a higher CO2 in the atmosphere, you increase the wattage, okay, and that increase will have an impact on the temperature of climate, okay. And this climate sensitivity is generally defined as a change in temperature resulting from the doubling of CO2. It is a standard experiment all modelers do to define the uncertainty in their modeling system, okay. Some models have a very high uncertainty, say for example 5.0 or 8.0. Some model has a very low uncertainty, say 0.8, 0.5. Okay, depending on the uncertainty range, they will estimate the temperature change. Okay. Okay. So what is the feedback? So the feedback process is the initial change in the process will tend to either reinforce, enhance, or weaken. So it could go both ways. It is not only one way, it could go both ways. Just to give you an example, if suppose you have a global warming and you add more CO2 in the atmosphere, it will further go higher. So something like that, okay? So it is a perturbation is a warming, and you have some feedbacks which is adding more warming, so it is going to increase the warming, okay? Other way, if you have some cooling system, say for example, you add aerosols into the system, aerosols tendency is to cool the system, and you add some processes which further cool the system, so it is going to further cool the system in that way. But if you add the greenhouse gases at the same time, aerosols, what is going to happen? So the warming will be dampened, okay, and this is the dampening effect. So the positive is balanced by the negative, okay. So you can imagine that we are adding more and more CO2 in the system, but at the same time there is some natural phenomena occur that will cool the system. So for example, this year, all my students are asking me, we are talking about the climate change, that climate is warming and our system is getting much more warmer. But what happened this year? Okay, and what happened? We heard all the way that our system is getting cooler, and this year was the coldest year in last 10 years or so. Why? Because there was some natural phenomena occur, what we call the La Nina year, and that's cooled our system. Okay, so there are balancing, the acts occurring in our system. Okay, okay. So what is happening when we make the projection due to these feedbacks? So these are the concentration of CO2 based on my model. Okay, over this next 100 years. Okay. And you see the scenario showed that the concentration varies from top to bottom. So for example, around current level is about 380, and it varies between here about 550 to about 900 parts per million by volume. Okay, but there is an uncertainty range. Okay, because there are a number of things. First of all, you understand the projections are very hard to make for CO2 emissions. So uncertainties come from the socio-economic aspects also, but at the same time, the carbon cycle also interacts with the climate change. Okay, as the climate is warming, ocean absorb less CO2, terrestrial ecosystem absorb less CO2, means more CO2 remain in the atmosphere. Okay, so you should expect higher temperature change because more in the atmosphere. So what is happening here is higher CO2, higher temperature change. So this is the temperature change. Okay, so higher temperature change will have an impact on the carbon cycle, means the CO2 concentrations. Higher concentrations will again have an impact. So there is a two-way interaction between these two systems. Okay, so it's kind of amazing. Nobody understands this. My student, when I talk about this, what they say is it really true? If we have a much more warming, we should expect much higher CO2 concentration? That's a fact, okay? Okay, so the biggest challenge for us is to understand these interactions. That's what I always talk about in my class, and students are quite fascinated. It's not only about the one component, biology component, or the climate system. We need to talk about the socio-economic aspect. We need to really understand how humans are behaving and changing our climate. What are the emissions? What are their behaviors making the emissions much higher? Okay, and then we talk about the concentrations, climate, carbon cycle, methane cycle, atmospheric chemistry, and then those interact with our radiative forcing, and then climate change, ocean, biosphere. All these are interacting. Okay, we need to understand all this. So in order to understand our climate system, we need a system which can take into account all these components and have interactions. Okay, so let's talk about the carbon cycle. Okay, the carbon cycle is the major, the cycle, and we need to understand, but the uncertainties are very large. And we always talk about the CO2 is the major greenhouse gas, but we don't understand how this system works. Very well, okay? So, just to give you an example why I talk about the CO2 is the major greenhouse gas, again, wattage per meter square change for individual gases is shown since for last 200 years, and these are the wattage per meter square change for the CO2, which is about 1.6 watts per meter square, okay? So there is a 1.6 watt per meter square change due to the CO2 concentration increase in last 200 years, okay? And this is the total change, okay? This one. So you could see that it's about the same. Okay, what is happening? There are a number of components. They are not only warming our system, but they are cooling our system, okay? So they are warming and cooling are balancing each other, okay? Think about aerosols. And if we don't have any aerosols in the system, you should expect much more warming into the system. Okay, we are talking about the controlling the local air pollution. So think about what is going to happen if you control the local air pollution, like sulfate aerosols or some other, the local air pollutants. You should expect much higher temperature in the near future. Okay, so this is the feedback. Okay, so the just basic question you can ask your students. So how much carbon dioxide emissions human activities are adding to the system? Okay, how much? This is very, very basic fundamental question. I asked my undergraduate grad student, they don't know how much humans are emitting today and what are the concentrations of CO2 and others. I mean, what was the concentration of CO2 in the pre-industrial time before the industrial revolution started? How much change have occurred so far in the last 200 years? Very few students. These are some very basic fundamental questions. So I hope that after the next slide you will understand what I'm talking about. And since all of the CO2 we are adding to the atmosphere is not accumulating in the system, so where it is going, okay? So just to give you an idea of what I mean by where it is going, we have a different component of the carbon cycle system. For example, we have an atmosphere, we have plants, soils, land cover and land use changes, and then we have a reservoir where most of the fossils are stored, and they have a large pool of the amount already stored in the system. For example, this big number is like 4,130 gigatons of carbon. When I talk about petagram of carbon or gigatons of carbon, that means 10 to the power 15 grams of carbon. Okay, this much is stored in the system. 1,500 in soil. It's a big amount. Okay, and similarly in the plants also above ground, the trees, leaves, they store about 500 to 600 gigatons of carbon. So there is a large amount of CO2 is stored in all these systems. Okay, then what happens? We deforest the land. Most of the CO2 into the atmosphere. Okay, if there is a warming, soil will decompose. Most of the soil carbon will be released in the atmosphere. So these are some of the processes. But then what is happening currently? Okay, what is happening is ocean also absorbs a lot of CO2 every year. Okay, due to the physical and the chemical processes. Okay, so what is happening every year? Ocean is absorbing on a global scale about 92 gigatons of carbon. 92 is a huge amount. Again, 10 to the power 15 grams of carbon. But at the same time, it released 90 gigatons of carbon. So how much is remain in the ocean? About 2 gigatons of carbon. So every year the ocean is absorbing 2 gigatons of carbon. Okay, before I go to the ocean, let's talk about the human activities. How much human activities are emitting in the system? About 6.3 gigatons of carbon is emitted due to the fossil burning every year. This is always based on the decade average. Yeah.
I'm quite getting one of your words. Are you saying gigatons?
Gigatons, or petagram of carbon.
Okay.
This is 10 to the power 15 grams of carbon. So you add 15 zeros in front of it. It's a huge amount, okay? Okay, so how much humans are emitting fossil on a global scale? About 6.3 gigatons of carbon. But not only that, but also we are deforesting the land. So this deforestation is emitting about 1.7 gigatons of carbon. Okay, so the total 8 gigatons of carbon is emitted in the atmosphere due to the human activity every year based on the average of 1990s. We always talk about the average because CO2 has a larger long-lived gas and we cannot emit the budget of the CO2 on a year-to-year basis. At least we need 10 years of time. So that's why always we talk about when we have to teach climate change, we always have to talk about 10 years, 100 years, or 50 years, long period of time. We cannot take any action on a year-to-year basis change. Okay? Okay, so about 8 gigatons of carbon is emitted by the human activities. About 2 gigatons of carbon is absorbed by the ocean. And then about 3 gigatons of carbon based on the current activities is absorbed by the plants and the soil. Okay, so what is happening in plants, about 63 gigatons of carbon is absorbed and the release is about 60. So remain is 3 gigatons of carbon. So you think about it, the balanced budget is about 8 gigatons. Okay, so how much is remaining in the atmosphere? Only about 3 to 3.2 gigatons of carbon, about 3 gigatons of carbon. So what is happening? 8 gigatons is released in the atmosphere, about 2 gigatons is absorbed by the ocean, about 3 gigatons is absorbed by the plants, and atmosphere has only 3.2 gigatons, about 3 gigatons of carbon. So this is the budget. Okay. So what happens? If suppose you warm the climate system, ocean is going to absorb less, more will remain in the atmosphere. Plants are going to absorb less, more will remain in the atmosphere. You should expect higher CO2 concentration. So this is the basic problem about the carbon cycle is the changes are so minor. It's very hard to measure. We can only model on a global scale. We cannot measure the fluxes, changes from one reservoir to other based on the measurement on a global scale. Okay, that's a basic problem. So we don't understand very well what's happening in the Southern Ocean, what is happening in the Pacific Ocean, what is happening. We have some number based on the measurement, but uncertainties are quite large. Okay, so this is the answer. Okay, so how much is emitted by the human activities, where it is going, it's already given here. Okay, okay, so let's talk about individual components. Okay, so the terrestrial ecosystem, we always talk about how much is absorbed, about 3 gigatons of carbon. I'm not going to go in more detail. Okay, just to give you an idea about what is happening, how we are perturbing our system. Okay, so there are a number of activities are occurring in our system. So I'm just showing you the change due to the human activities and all other natural activities over the North America. Okay, here the colors are red means release in the atmosphere, green means absorbed by the plants or the ecosystem. Okay, so it goes both ways. It's not a one way. Okay, because plant also absorbs CO2, but there are a number of processes occurring that also release CO2 in the atmosphere. Okay, what kind of activities are occurring? So this is for the US and Canada, North America. Okay, so the red are release and green are absorption. Okay, so what kind of activities we talk about in terrestrial ecosystem? Land cover and land use changes. Okay, land cover and land use changes, you think about always release CO2. Okay, because deforestation. But what is happening is also plantation, okay, reforestation, afforestation, but then also there are interactions. Higher climate change will have a feedback with the plants that also would absorb CO2 or release CO2 depending on the region. Okay, climate has a big impact. Okay, higher climate is going to have a big impact on the soil carbon. Higher climate change means more decomposition, more release in the atmosphere. But in some area, there is a colder climate. You could expect, the absorption of CO2.
What do you think about the theory that deserts are absorbing CO2?
I have no idea.
Okay.
I would not. This is a very uncertain area.
Yeah.
But first of all, there is not much CO2 in that region. Desert has no. There are no soil or nothing.
Well, there was an article in Science magazine last week about deserts actually sequestering CO2 in large amounts. So I don't know if you've heard about it.
No, I haven't heard. I think this is something I've heard from my students. They talked about this article, but I have not looked at this article. But there are some plants in desert, okay, and they could have an impact, but I can't imagine that the desert plants or the desert soil, whatever is going to have a big impact. Okay. Okay. Another aspect is like CO2 fertilization, higher CO2, higher plantation growth. That will have an absorption of CO2, nitrogen, deposition, also fossil burning also release nitrogen, which is also fertilizer, which also increase the productivity. And the forest fire, okay? All these factors could change our, the ecosystem. And all these are interacting. So this is the net of adding all these things. But it's not a one way. You cannot just add the effect of each individual and you get this because of the interactions, okay? So you can do all this using the model. So this is what I'm showing you based on my model, okay? Another aspect is sequestering carbon in soil. For example, you might have heard that the farmers are using some management practice like no-tillage, and that has an impact on sequestering carbon, particularly in North America. And this is what I'm showing here based on the models results. And we publish in a paper which shows that this region has a much higher sequestration potential. Okay, so there's a lot of amount can be sequestered in soil, but again, the effect of climate change could reduce or increase this sequestration potential, okay, depending on the warmer or the colder climate, depending on the region. Then what I'm showing here is the change in terms of percentage, say for example 25% higher sequestration and about 15% lower sequestration due to the climate change. So there will be a sequestration due to the no-tillage, but the climate could dampen or enhance that sequestration rate, okay? So if you look at this over the latitude, how the terrestrial ecosystem are behaving, some latitudinal regions are releasing carbon, some are absorbing carbon. So always the negative is absorption by the plants and the positive is release in the atmosphere. And when we talk about the climate change, we sum up all these changes and get some single number and say, okay, this much CO2 is released or absorbed by the plants, okay? And there are a number of processes like land use, climate, CO2, nitrogen, biomass, burning, management. You have to take into account all these factors, okay? Okay, so these are the numbers which I'm not going to go in more detail. I mean, they have no meaning actually for you guys. But just to show you, fire and the nitrogen and the management are some crucial aspects to understand the terrestrial ecosystem. Okay, we always talk about the land cover and land use changes, CO2 and climate, but the fire is a major source of CO2. Nitrogen is a major sink of CO2, and the management is also an important sink of CO2, particularly in North America. Okay, let's talk about the ocean. Okay, when we talk about the oceans, ocean absorbs CO2 in certain regions and then release CO2 in certain regions. I'm sure that David Archimers have talked about the downwelling regions and the upwelling regions. So these are the regions where most of the CO2 is downwelled in the ocean, and then it circulates. The whole cycle is about 10,000 year cycle. Okay, if you inject the carbon a unit amount, it will take about 10,000 years to come back to the same point. So it is about 10,000 years of cycle. Okay, at least 10,000 years of cycle. We always talk about 200, 300 years. So it has a long, long lifetime. Okay, and this blue color is sinking regions, and the red one is the upwelling regions. Okay, and there is a cycle. There is a the standard circulation process, what we call the thermohaline circulation, and that's what it's shown here. So you have a standard circulation pattern that the water flow from the Southern Ocean to the northward, and then it downwells, and then it move again towards south, the southern hemisphere, and then go back to this. So this cycle is actually circulate the CO2 as well as energy. But what is happening due to the climate change, that you should expect less downwelling of CO2 in the higher or sinking regions. So these are some of the sinking regions. Okay, we have a salty water. You think about it, that higher temperature change, lesser density means lesser penetration of CO2 or energy in the sinking region. Okay, just to show you what we mean by the salty water, we always measure the salty water in terms of the salinity. Okay, and these are all measurements which I'm showing you here, and these are the higher latitude. Okay, and this area, this color shows the less sinking, and this color shows more upwelling. Okay, so what you see here, this area, higher latitude, 60-degree latitude in northern hemisphere, and 80-degree or 80 to 40 degree is about in southern hemisphere, where we have a less sinking, more remain in the atmosphere, and here it's upwelling. Okay, so this is based on the measurement. The measurement shows the water is getting less and less salty, that salinity is reducing, more is remaining in the atmosphere. You should expect then the interactions. So higher CO2 in the atmosphere, more climate change, less absorption by the ocean, vice versa. So it's going on. Okay, so just to show you some of the results of these impacts using the simple model. Okay, we have done some analysis to show what will be the impact of all these climate interactions on our, on the CO2 concentrations in the atmosphere, or absorption of CO2 by the ocean. Okay, and we have a simple model which takes into account the major processes and everything. I'm not going to go in more detail. So these are the results. Okay, so you might have heard about the stabilization scenarios that the policymakers are now suggesting to stabilize the concentrations of CO2 and other gases at a certain level. So this is one of the stabilization scenario we developed for the Intergovernmental Panel on Climate Change, what we call the stabilization of CO2 at about 1,000 parts per million by volume by 2500. Okay, so these are the concentrations around 1700 or so, and then it is increasing, and then it increased steeply, and then stabilized. So these are the concentrations. So what are the implications of these concentrations on surface temperature change? You should expect the temperature to rise this way, depending on the climate sensitivity. The best estimate is about 2.5 degrees Celsius estimate, and based on that climate sensitivity, the temperature will rise around 19 degrees Celsius. But then what happened? Higher temperature change, what is going to happen to the sinking region? Okay, how much CO2 will be sinking in that region? What is going to happen? That the circulations get slower down, what we call the northern Atlantic overturning is slowed down, and the sinking gets just completely go away. I mean, we don't have any sinking. So all the CO2 after around 2200 remain in the atmosphere. This is just a simple experiment to show what will be the impact of global warming on the absorption of CO2, particularly in the high latitude band. Okay? Okay, just to give you an idea, what are the other implications in the ocean? So you have the nutrients, actually, which takes the CO2 in the deeper of the ocean. Okay? What we call the export production. So most of the production will be slowed down, and most will remain in the upper part of the ocean, and this much will be reduced, the CO2 absorption by the ocean. So there will be a big impact on the absorption of CO2, and based on this scenario, about 290 petagram of carbon will remain in the atmosphere. Okay? So there is a big impact due to the climate change on the absorption of CO2. Okay. Also what happened that as we add more and more CO2 in the ocean gets more acidic. Okay. So what is going to happen then, you should expect, okay, this is another the same scenario. You have a higher CO2, higher hydrogen ion concentration. That means pH gets smaller. That means the water gets more acidic. Okay. And these are the numbers showing the pH reduced due to the higher CO2 concentration in the ocean over the time based on that scenario. But also climate could also interact and have an impact on the pH. It is showing the range of values, but there is not much change. I will show you over the the latitude how it's going to change over the time. But there is going to be a change in the pH due to the higher CO2 concentration. Another aspect is Urbana-Champaign, that is calcium carbonate, which forms the skeleton of calcium carbonate helps to form the skeleton of corals actually. So what is going to happen? We should expect less calcium carbonate formation, means we can have an impact on the coral formations also. So higher hydrogen ion, less carbonate, less formation of corals, skeletons. Okay, so these are some of the impacts. Okay. These are the changes over the time starting 1800 to 24 for pH over the time. So current change is about 0.1 pH, okay? And over the time it would change up to say about, in the deeper of the ocean, about I think 0.5 or 0.6, okay? But most of the effect will occur in the argonite, that is the calcium carbonate, which if it reduces, then the formation of the coral skeletons will be affected. There are some other effects also of these changes. For example, lower pH, reduced calcification, that's calcium carbonate, and reduced argonite, and also reduced respiration, blood circulation, and the growth of fish. Okay, higher temperature change, bleaching of coral bleaching. So these are some of the effects which have been proposed. Okay. And we have not done this study, but if our model results give the reasonable answer, then we could expect these kind of changes. Okay, let's briefly talk about how much time? 10 minutes. So I don't have much time, but I'll go through this very quickly about the web interface of our model. So it is integrated sciences of the model. As I have mentioned, that it takes into account the interactions of the number of the components. We talk about the human activities, ocean, terrestrial biosphere, all those kind of aspects, and then study the interactions. Okay, so it is a very basic, simple model. Okay, it takes into account the basic emissions on a global scale. It calculates the concentrations, it calculates the temperature, it calculates the radiative forcing, it calculates the sea level rise. You can do all those things. In addition, it also calculates the stratospheric chlorine, bromine, and change in ozone. Okay, CFCs are the greenhouse gases, but they also impact our stratospheric ozone, the good ozone. Okay, and it also calculates that amount of ozone in the atmosphere or in the stratosphere. Okay. Okay, this model, just to give you an idea, but this model has been used for the Intergovernmental Panel of Climate Change Studies of Carbon Cycle projections for several scenarios. Okay, and these are some of the scenarios. We did this for IPCC, projections of emissions and what are the impacts of the emissions in terms of concentration, and then stabilization scenarios, which I have just discussed. One example of 1000. Okay, so just to show you some of the things, how it's going to work. Okay, this is the website for my model, okay, and it is called the ISM Interactive Internet Interface, okay. So there are a number of things you need to have, for example, what goes in, emissions of major greenhouse, as well as then the model calculates the concentration. Just to give you an idea, And please write down this website. I also have on my notes. You can actually look at that. So, for example, we talked about there are a number of things you can do with this. Okay, you have a tutorials. You can go through the tutorials and understand how this web interface works, and then you can run the model without making any changes. You can run the model. Okay, but in order to understand, first I just want to make some changes, okay, to show you how the climate system, what we talked about, 1.5 to 4.5 degrees Celsius change will have an effect on scenario or particular scenario and the temperature change. Okay?
Excuse me, let me ask. Is this website listed on any of our material that we're getting?
No, but I didn't have it before just now, so but we'll post it on the website as a
So we don't have to copy this.
right as an updated. I'll send you an email once it's all updated.
Okay. So you can select the model and period. So for example, there are a number of models, but at this time we have only one version of model. Always you have to mark that model. Okay. And then you can run the scenarios up to 2200. So I have set up to 2100, and then you just click this and it will store it. Okay, and then you can also change the parameters of the different model components. So for example, carbon dioxide we talked about, and then there is the methane cycle, and then the climate ocean model. So climate ocean model actually controls the climate sensitivity, what we talked about. Okay. Just to give you an idea how the emissions look like, okay, about the models, parameters. So this is the ocean component and the terrestrial component of the ocean of the carbon cycle. Very simple, basic model. It has different components. For example, velocity, operating velocity, vertical diffusion, how much is the net primary productivity, mixed layer depth, ocean parameters. And then industrial, pre-industrial CO2 concentration. Similarly, you have a component for the terrestrial ecosystem. Okay, and then you have climate ocean models. We talked about the climate sensitivity, say for example, change in CO2 temperature change due to the W of CO2, and I have fixed it to 2.5. So you could change this climate sensitivity from 1.5 to 4.5 to see what will be the impact of this uncertainty range on the temperature, which I will just show you. Okay, say for example, I will keep it as 2.5 at this time and then store it, and then you can change the emissions for all the gases. Okay, so you have the emissions for CO2 fossils from starting 2000 to 2100, land cover and land use changes, methane, carbon monoxide, NOx, volatile organic carbon, N2, nitrous oxide, and the sulfur dioxide, which is aerosol. Okay, and you have also some standard scenarios. So these are some of the IPCC standard scenarios. So for example, you can click any of the scenarios here, and it will change the number. Okay, and this is the basic IS 92A, what we call a business as usual scenario. Once you click the numbers, or you could change the numbers as you wish. So here you could change, you can develop your own scenario for CO2 or for methane or for any other gas. You just change, you add or you just replace the number by your scenario, and then just click it. Okay. Okay. It's stored. Now you could go and run the model. So what is happening now? The model is running on my server, okay, and it's done. Okay. Now you could see the results also. Okay, there are a number of things you can actually look at in terms of results. So CO2 model results like CO2 emissions, CO2 concentrations, all the emissions you have described, carbon monoxide, hydroxyl, greenhouse gas emissions, concentrations, sulfur dioxide, all these things. But what you have to do is, you have to, okay, you can run the model number of times, and each time you run the model, you have a run number. You can, you can note down your run number and go back and look at your results based on the run number. But always you have to mark that, okay? And then, for example, I could look at the temperature change. Okay, and get the result. So it will show you the results, okay? These are the changes compared to the 7065, that is the pre-industrial time, and this is for the certain time period. Scientists are always interested in the average over the certain time period. And then some of the scientists are interested in compared to 1865. So if I have numbers for different, in the different form, all in degrees Celsius, okay? So you could get all these numbers, okay, up to 2100. So for example, based on that IS-92A scenario of climate sensitivity 1.5, you get about 2.3 degrees Celsius change by 2100. Okay. So you could do this experiment for 3 climate sensitivity. We talked about 1.5, 2.5, and 4.5. Okay. So I have already done this exercise just to show you how the numbers will look like. Here. So I have done this case for 3 climate sensitivity, 1.5, 2.5, and 4.5. This is the range of uncertainty. And then you see in IPCC the change in temperature by 2100 based on one single scenario. Always you see the range. Okay? It changes between 1.5 to about 3.7 degrees Celsius. So this is the uncertainty range in the temperature change due to the IS-92A scenario. Okay? Calculated by the model, and this is the uncertainty based on this different climate sensitivity, based on the different climate in the 2005. So you could do all those kind of experiments. You can also estimate the sea level rise based on the different climate sensitivity. You can do all those things, okay? And if you have any question or concern, feel free to contact me by email. I will be happy to provide you with the answer to your question. Thank you.